Hey everybody, it's Mr. Worden coming back at you with a new lesson. This one's going to focus on transistors, logic gates. We're even going to go as far as a little bit of Boolean logic and how that happens, as well as basic arithmetic and binary. So let's jump right in. Like I said, we're going to do a quick chemistry and physics review so that we understand the basics of how transistors work at kind of a deep level. We're going to go through a bunch of vocab describing how they're built, how they're set up, how they operate. Those form the basis for logic gates, which are basic Boolean logic functions. And with Boolean logic gates, we're going to make sure we understand them in a couple different ways by drawing out circuits representing them using truth tables with ones and zeros, and also just some classic old school Venn diagramming. And with enough logic gates, you can actually start to build the most basic structures in a computer. We're going to go through how to add and subtract binary in up to an 8-bit register. So that's pretty much it. Let's jump right in. So first up, let's get some chemistry and physics review. Let's see, chemistry. Okay, periodic table. Staring at this thing. Each of these different elements has a different atomic number, and that represents the number of protons in the nucleus. In addition, it's got the total contents of the nucleus as the atomic mass, and that's the protons plus neutrons. So for example, for helium, it's got 2 protons, and then an additional 2 neutrons will bring the total in the nucleus up to 4. And you may remember as well that we're going to assume that these atoms are neutrally charged, meaning that the positive protons and negative electrons are equal. And so we're going to assume that this helium here has 2 electrons as well, and that total charge balances out to 0. Now, because electrons are able to move around in chemical reactions, that's not always the case. Some can take some electrons and acquire a negative charge, or some can give electrons away. And by losing that negative charge, they end up with a positive charge. We would say that those are then ionized. So we're going to talk about neutral or ionized atoms. Now, one thing that atoms tend to do is they tend to want to fill up their outer shell. And a shell is an electron layer made up of multiple different orbitals. And you can pretty much look at the periodic table and you can see the shells as the same thing as a row. So for example, helium has only 1 shell, whereas neon has 2 shells. Has an inner shell with 2 electrons, 1, 2, you can just count tiles, and has an outer shell with 8 more electrons, which brings the total up to 10. Now, atoms are most stable when their shell is either totally full or totally empty. And this is true of most of the elements on the left side of the periodic table and the right side of the periodic table. This yellow section called the transition metals, it's a little more confusing. They can't necessarily move that far over, so they'll have a bunch of secondary rules for how they tend to ionize. It gets a lot more complicated. Anyway, good news, we don't really have to mess with that. We're going to be looking mostly at silicon and germanium, as well as its neighbors to the right and left of those. So we're going to actually notice that there's a pattern here where the element at the top is a pretty good representative of the rest of the group below it. Group means column. So what carbon does is something similar to what silicon and germanium and some of these other ones should do as well. And carbon, right now it has 6 electrons. In order to completely fill up its shell, it would need to take 4 more, 1, 2, 3, 4, to be like neon, at which point its second shell, called the valence, is totally full. Or another thing it could do is it could give away 4 electrons, 1, 2, 3, 4, to be like helium, see 6 down to 2 or 6 up to 10. And at that point it would be a +4 ion. Now, in reality, what carbon is going to do is it's actually going to share out its 4 electrons with somebody else's 4 electrons. And by sharing, they can feel like they have a full set of 8. So it's basically going to pretend like it's taking electrons, but actually it's sharing them instead. So it doesn't necessarily acquire charge. It can still be neutral, but it feels like it's got a full set in the process of sharing, and we call that a covalent bond. So carbon basically needs to share 4 times. Silicon, same thing. It wants to be like argon, wants to have the same noble gas configuration of electrons. So it's going to share 4 times, just like carbon is. Same thing with germanium. What it's typically going to do is share 4 times. So they're each looking for 4 electrons and 4 connections that way. Now, if I were an element 1 to the right of silicon, like phosphorus or arsenic or antimony, what I would be doing is only sharing 3 times. I have 1 extra electron compared to silicon. Or if I were an element to the left, like gallium or indium, I would need to share 5 times. And compared to silicon or germanium, I'm missing 1 electron. So this is going to be important later. Okay, 1 to the right, they have an extra electron. 1 to the left, they're missing an electron compared to silicon or germanium. Now you might know carbon because it shares in 4 different directions, or can share 4 times total, sometimes it'll do a double bond, share twice in the same direction. It can make a whole bunch of cool different arrangements, like diamond, like graphite, like Buckminster fullerene, graphene. It can be amorphous, like coal, which means no particular shape at all, just total chaos. So there's a bunch of different arrangements it can set up in, but you can basically think of this as having the possibility of crystallizing out in some kind of a repeating geometric pattern. And the same is true of silicon and germanium too. So one thing we can do is we can take pure elements of silicon or germanium, and we can form a pretty big crystal array where the way that it's sharing makes a nice geometric pattern called a tetrahedral. So there's just some kind of chemistry things to know about. All right, moving right along, let's talk about some physics ideas. So first up, one idea is that the energy in an object can be because the object is moving, either on a large macro scale, like if I throw something, that we call that kinetic energy, or it could be moving on a really small scale where each individual atom or molecule is wiggling inside some bigger solid, liquid, or gas, or some other state of matter, and we'd call that thermal energy. Another option is that an object can just have a position within a field. For example, if you have a brick on the floor, that's as low as it can go, and I would not say that that has any potential energy. Potential energy is energy from its height inside the gravitational field. However, if I lift that brick up like 2 feet off the floor, I've just put energy into that brick. It has potential energy now. So I would call 2 feet off the floor an excited state, and I'd call on the floor a ground state, literally because it's on the ground. That's as low as it can get. Now that is for mass in a gravitational field. Another thing we could talk about is these electrons. They're getting pulled and attracted by the nucleus of an atom because opposite charges attract. And that's electromagnetic forces involved on charge instead. And so if I take an electron as low as it can go, the farthest down orbital that it can exist in, and if I give it some energy, one thing I might do is I might lift it up farther away from the nucleus. And then also I could let that electron fall back down, and in the process it would have to give that energy up and release it. Like you guys know, if I drop the brick, it's going to get kinetic energy while it falls. After it hits the floor, it's going to shake and vibrate the air on the floor and maybe even do some damage. And that's all going to be thermal energy or energy in broken chemical bonds or something. So that energy doesn't just disappear. It goes somewhere. It converts into some different form, oftentimes thermal. And we can see like falling electrons near atoms. Often one thing they do is they give off light. So a lot of our different light colors come from electron falls. Or they could show up as thermal energy. The atom gets more wiggly or something like that. Anyway, what I got right here, pretend these are soccer balls or electrons or whatever. And there's some field on the y-axis. And this is just position on X. And you guys can tell that ball number 1 is in a stable state. Like ball number 1, if I let go of it, it's not going to do anything. Same thing with ball number 3. Ball number 2 is unstable. And if we give ball number 1 some activation energy, we get it going, we can lift that thing up, get it to position 2, at which point it'll release its energy even more so now that it's dropping down to a closer to the ground state. And in the process, that energy will get released. This will become even more stable, sitting as low as it can go. So this diagram here is called an energy well diagram. I like to think of soccer balls in between 2 hills. Like, oh, yep, we know the soccer ball is going to roll down and end at the bottom center there. That's just one thing to think about. Like, if these were electrons instead of soccer balls, and we're talking about electric fields, where would they go? How would they tend to settle down? So that's something to keep kind of in the back of your head. And at the right, we got just an electric field diagram. If we had a positive charge, it would get repelled by like, and it would get attracted by opposite. Or if I put an electron in here, it would get attracted towards positive and away from negative. And typically it's electrons that are the thing we think about moving. So I would say if I put an electron here, it's going to start to accelerate to the left from all the force on it in that field. So that's kind of just quick physics review on some energy concepts in general. Might help out a little later. And last up, since we're talking about some circuits and electricity, let's review some kind of most basic stuff. First up, we got voltage, which is kind of like how hard the electron's being pushed across the circuit. We've got current, which is how much is flowing per second past a given point. We got resistance, which is the difficulty of passing through that material or circuit element, which in the process is going to consume voltage and consume power and convert energy into thermal form. That's going to kind of limit how much current can flow through there. Like think of a restriction through a set of water pipes. It's going to limit the amount of current flow. And then lastly, power is how quickly energy is delivered or how quickly energy is transferred. So this is the rate of energy delivery. And they're measured in volts, amps, ohms, and watts, respectively. So with that kind of legend right there, let's take a look at these 2 equations here. The first one's called Ohm's law, most important equation in electronics. Voltage equals current times resistance. So basically, like if you push harder, you can get more current to flow. But if you restrict it, you're going to get less current to flow. And that's about it. Enough said. This other one says that power is how much is moving past a certain point times how hard it's being forced through. It's not exactly the same as force, but think of it that way for now. And so that'll generate our watts value, our power energy delivery per second. Okay, other stuff we should mention. Here are some different symbols. We're mostly going to be working with transistors, and we're going to be ignoring a lot of these, even though some of these are in the circuits we're going to be discussing. We're going to simplify a lot of our circuits down to just transistors, maybe some voltage sources. Oh, you know what? The one that we need that's not on here is ground. So let's see. Let's make sure we get symbol for ground. Oftentimes it looks like that. Sometimes it looks like a fork you literally stick in the ground. So these are both ground. And when something is grounded, it's at 0 volts. So you're basically providing a place for electricity to go and zeroing out any remaining electric potential on that. The other thing we'll do is we might not always use like a voltage supply symbol. That's like a symbol for a multi-cell battery, but we can use it to indicate a DC voltage source. We might just put a terminal on. We might just say like +5 volts and have that terminal go somewhere. So we might call this high voltage. We might call this low. Not like high voltage isn't a lot of volts, just this is the high source and that's the low place that it can sink down to. So we might contrast like energy comes in from here and dumps out to there. And one thing to think about is that a wire doesn't really have any significant resistance, at least not if it's a good wire. Hopefully it's got almost no resistance. And what that means is the voltage across the wire is the same across that entire segment, maybe until we get to some other circuit element. And then maybe there's a drop across that element that does have resistance. We might get a different voltage on the other side. We're working with the idea of what's called an equipotential. Potential is kind of a synonym for voltage. So we're saying across the wire, the voltage is all going to be consistent, which means if you ever see a wire tied to ground, that entire wire should be 0. Or if you see a wire tied to that +5 voltage power supply input, that entire wire should also be at +5 volts. Last up, switches. Closed means that we have a metal-to-metal contact, no resistance, or at least almost no resistance, and we're going to get a lot of current flow. And so I'd consider a closed switch on. And then an open switch, that's when we got the metal-to-metal contact is opened. There's an air gap. Air is an insulator, very high resistance. And what that's going to do is drop the current across that to basically 0. And that's when we would consider something turned off. That was a super quick crash course on a couple physics and chemistry concepts you've probably seen before in other classes. All right, so now I think we're good to go here. Let's jump to transistors. All right, step 1. We're going to take a giant silicon crystal, totally pure as you can get it. These are typically produced on wafers. So there's this big rod of silicon crystallized, and they'll slice wafer real thin discs out of it. And you take this wafer and you get like a mask over it, which is kind of like a stencil. And they will optically etch or deposit or burn different parts of it using lenses to focus this images down to really, really small scales. So if you want to learn more about the manufacturing process, it's pretty awesome. And the things they're having to do these days to build super, super small ones on the nanometer scale is pretty amazing. Anyway, got this totally pure silicon setup. What we're going to do is we're going to create P regions or N regions. P stands for positive, and this is where we would dope it or inject some impurities on purpose, where they're typically atoms with, let's see, 1 fewer electron than they should compared to silicon. So thinking back to our periodic table, P-type doping would be 1 to the left of silicon and germanium. And so we're typically going to use gallium or indium for that. These 2 elements right here would provide P-type doping, where we're missing an electron, and instead we got just kind of an extra proton hanging out once they try to link in with all that. And then opposite, N-type doping, is where we have an extra electron, and that's where we're going to use arsenic or antimony or something like that to dope. And these have 1 more electron than silicon and germanium, the thing that we made the crystal out of. So the crystal's all set up for these, and by putting in some impurities in, either with a missing electron, we can create a hole or a pocket for some electron to accidentally fall into, or we can create that extra electron that kind of needs to go somewhere, and it's hopefully free to move around within the crystal structure. And when it moves around, we call that migrating. So here you can see we got a section that's p-type, we got a section that's n-type, and what happens is at the junction between the two, we're going to have some of those extra electrons from like arsenic fall in and occupy the hole as something like germanium or indium. And when they do that, all the atoms before this happened were neutral. But now that an electron has left the n-type, it doesn't have the same negative charge that it used to, and that leaves behind positive. Because now the protons outnumber the electrons where the electron left from. And then when it falls into the hole, now the place that had a hole suddenly has an extra electron showing up, and that's going to put negative charge there. So at this junction, we're naturally going to get an electric field produced across that junction as free electrons migrate into holes across that boundary. Now, the electrons in there, they're pretty stuck. And those free electrons that we're able to move, they're stuck. So across this junction, we've got what's called a resistive band. We got some resistance here where it's really hard to move stuff across that. And if we push even more free electrons into the holes by putting some charges on either end of this, which we call biasing, so apply a voltage across this. If we push more electrons in, we can get things more and more stuck, and that resistive band is going to widen. We're going to increase the resistance of this circuit element. Or if we bias it the opposite way, let's say reverse bias or something. Actually, I have to think about which one's which, but okay. If we push on the opposite way, maybe we can narrow that resistive band, and we can keep everything free and stuck out of the holes. So by changing the size of the zone where stuff has fallen in and gotten stuck, we can modify the resistance of this path across that circuit element. By modifying the resistance, we can also control the flow of current. Now, what you're looking at right now is two different regions. And two different regions, when you set it up this way, it's called a diode. Di means two, right? So diodes have two regions. And we can pretty easily see, oh yeah, if we push one way, we narrow this thing. If we push the other way, we widen this thing. So what this is going to do, a diode is going to be a great way to set up a one-way valve. Electricity can flow one direction, but it gets stuck if it tries to go the other direction as the resistance increases. So they're kind of a cool circuit element for that sense. And they even have a symbol. Go back to our symbols. You can even see that they've got a symbol like a one-way valve. So here's a light-emitting diode, LED. Here's a regular diode. And you can tell, oh yeah, there's a one-way valve on circuit just from the way that circuit element is drawn. Now, a transistor is a little different from a diode in that it's got free sections. You can either set the sections up as NPN, or you can set them up as PNP. And remember that the N's and P's refer to which type of doping you did, whether it was with an extra electron for N-type, or whether it was missing an electron and therefore has a hole for P-type. So problem is we're going to get multiple stuck sections, and if we just push one way with either a forward bias or a reverse bias, we might shrink the resistive band at one junction. We're going to do the exact opposite and enlarge it at the other junction. So either way we push across this thing, we're going to get stuck. But fear not, there is a third place you can put a current across and put a voltage across. So basically, they're going to give you a third wire to control a current across the center and get part of this unstuck enough that it can make it across the second one too. So by controlling the middle piece, you can actually control both sets of junctions. Now, vocab words for these, they typically have a name like the inside, the outside, and something to do with switching this on or off. So in this case, this one's called emitter-based collector. There's another one called source, gate, drain. And let's see, which side do you think electrons are coming from? Oh yeah, the emitter side. Which side are they going to? The collector side. Base controls how that works. Or source, gate, drain, same thing. You can think through which side's going in, which side's coming out, and how we control that. Now, a couple different kinds of transistors. You could build really, really big ones. And the big ones kind of pictured here, those are great if you're dealing with a lot of current, a lot of power, and in the process generating a lot of heat. You don't want these things to melt. And so you need a physically large one to be able to dissipate heat and handle that power throughput. And a lot of times we'll use these in an analog setup to do things like build an amplifier. So if you want to crank your 1000 watt stereo, you need a giant transistor as the core of that to be able to handle that. On the other hand, if all we want to do is have these things flip on to off with the least power possible, least current, least voltage, operate super fast, then we're going to do the exact opposite. We're going to build these as tiny as possible so we can fit many complicated gate patterns on a single tiny little microchip. And so you can see this is some images from an electron tunneling microscope Intel took of their 22 nanometer tri-gate resistor. This is an old photo. People are working on like 7 and 10 nanometers and even smaller sizes now to try to get more transistors per chip, which makes the chip be able to do more and effectively be more powerful. And the smaller size, you can also oftentimes push a smaller current, lower voltage, and just be more efficient and eco-friendly. By the way, here's a symbol for it. You notice it's got 3 wires, right? Because we've got this middle piece right here to control whether this goes on or off. Now, at this point, I recommend opening a new tab, hopping on YouTube, and playing this tutorial right here. This thing is pure gold. I love it. Always get a giggle out of it. And it does a great job kind of recapping the same things that we just talked about with super high-end graphics and stuff like that too. So shout out to whoever made this. This video rocks. Check it out. Pause the video, put in this URL. It's worth it. Good stuff. And then we'll jump right back in. All right, so hopefully you did that. Should have paused it and checked this video out. It is awesome. Good stuff. It talks to a little bit about analog versus digital operation of these. Anyway, let's carry on. So there's 2 different ways to manufacture this. If you're in the IB course, you do not really need to know the difference, just that they have different names, little bit different configuration and setup. Generally do the same kinds of things though. If you're a little more savvy on your circuits and you remember stuff from physics, these arrows represent conventional current. And the operation of a PNP transistor is exactly opposite of an NPN. So like PNP would turn on when you apply a low voltage to the center, whereas an NPN would turn on when you apply a high voltage to the center. So we can build them opposite on purpose to do different jobs. Now, we are ready to dive into logic gates. It's going to be the fastest crash course ever. Here we go. Okay. We're going to skip this for a sec. We're going to switch to like doodle it out mode. Let's say I had 2 inputs, A and B. First of all, these are going to be either true or falses, and I can represent true or false with a 0 or 1. So 0 is false, 1 is true. And I want to know what all possible combinations of inputs there are. Good news, this is going to look like a bunch of 0s and 1s. It's binary. Whenever you're constructing this chart, which is called a truth table, please enter your inputs in order as if you're counting up in binary. If you do it out of order, all of us that are used to seeing these things are going to get super confused at what you're doing. So please always do this in order. There's 0, there's 1, there's 2, and there's 3. And now I've covered all possible input combos. Now, that's going to be true of most of these logic gates we're looking at, just kind of a set of inputs of 2 things. We're going to have an output C, and I want to know what function I'm talking about. So let's pick a function called OR. What I'm going to do is I'm also going to draw a Venn diagram, although if you want to be super chill about it, you can make a Zen diagram. Imagine this as your sand and gravel, a little bonsai tree, a little stream. Anyway, we're going to label this A and B, and I want to know if OR, it could be in A or B, right? Like if it's in A, that's fine. If it's in B, that's fine. This particular OR, it can also be in both. There's a different function called exclusive OR. Let's talk about that later. Anyway, I'm going to shade this in. A is happy. Get your rake out, rake the gravel. I think when B, we'll do like a real cool swirl pattern. Probably hard to do in real life, actually, now that I think about it. Swirling with a rake. That's next level. Okay, so any place I shaded belongs to the function called OR. If I didn't shade it, it doesn't count. And so let's just read this off. When it wasn't in A or B, oh yeah, that's this outside region right here. Don't forget about that. That was not where I shaded. But I did shade the part that was just B. I did shade the part that was just A. And I did shade the part that was both A and B. There we go. We have a Venn diagram. We have a truth table, both for the function OR. Let's distinguish now between OR and exclusive OR. Exclusive OR, also called XOR, that's when we don't include when it's both. We really just mean one or the other, but never both. So if I modify my Venn diagram, what would I do here? Which of these needs to change? Oh yeah, what I'm going to do is I'm going to switch this out for a 0 right there. All right, done. Let's do AND. Keep that. Oh, what the heck? Let's make this again just for practice, because otherwise those guys that forget are going to do this out of order. I'm going to be grading your test. I'm going to be all super confused. We're going to count up in order in binary. Hopefully you watch the binary tutorial if you need to, or you're good to go on that already. Anyway, and make the Venn diagram here, A and B. And is when it's both, right? Darn it, I didn't get to do a lot of shading. We'll just go real dark on that to make up for it. Okay, cool. So that's the part that counts as and. And that was only when it was both. There's my output for and. Now, if you put an n in front of this, that's not. You are looking wonderful today. Not. You did great on the tests. Not. Well, that's pretty harsh. What not does is it makes it exactly opposite of whatever had previously been happening. So exactly opposite would be any 0 becomes a 1, any 1 becomes a 0. There is not and. And if I were to shade this, we'd shade that, we'd leave the middle blank, and I just made a mistake. Hopefully you're thinking, oh, don't forget the outside. Sometimes people forget the outside. That's a thing, right? That's the 0, 0 condition. Hey, you can have just a not. The not doesn't need 2 inputs, though. It only needs 1 input. So I just go from A to B. Now, if I put in a 0, and I get out a 1, there's a not function. And there's a bunch of functions. Let's take a quick look at my top list here. So what you're looking at is a truth table for each of the most common functions. And you're also looking at the official symbol to represent that function. That's only somewhat abstract, is pretty basic. Each of those things is typically about four transistors and a couple resistors, 2 input wires, 2 power wires, and an output wire. So a bunch of wires. We're going to take a look at those in more detail in just a second. But yep, if you need to reference this, just Google it. If you're taking an IB test, I think they accept circles with the name of the gate written in if you don't have the actual symbol memorized. But, there's some cool stuff here. The little circle right on the end of this, right here or right here, that's the not part of it. So you can see the N in front. Yep, you can see that they're related. So, yep, that's about it. Okay, now why do we care about these gates? Oh, by the way, you should be able to use the gate, use the truth table, use the Venn diagram. The 3 things, you should be able to quickly switch between the 3. Interpret this all the different ways. Now, how do we get one of these gates, and what does this have to do with transistors? What we're going to do is kind of look at tracing this, and I like to trace them exactly backwards. So we're going to look at an AND gate first. And actually, I'm going to just draw this out real quick. Once you get the hang of these, they're not that hard to draw. So I'm going to always start with a high voltage input up at the top, and I'm going to have a ground down at the bottom. And I'm thinking backwards in how to do this. And I'm going to have inputs A and B, and I'm going to have an output C. And my goal is to make sure that C gets either plus 5 volts under some set of conditions, or it gets grounded and has 0 volts under other conditions. By the way, I just picked plus 5. Depends on your actual processor and stuff, what that voltage is. Some voltage that's not 0. And that's just a terminal shape right there. Okay, so let's see. Let's do AND. For AND, I know that my truth table, let's see, let's make that truth table real quick. Here's my wires. And when these 2 are off, that doesn't count. Counting up in binary. And that doesn't count, and that doesn't count, but that does count. Or another way to represent this is A and B. I only want that part to turn on. So only when A and B are on should C connect to high. Otherwise, under any other condition, C should connect to ground. So I'm gonna set up 2 transistors in parallel. And I'm also going to set up 2 transistors in series. There's my transistors. And I chose that arrangement so that it's easy to get to ground, but hard to get to high. So I put the parallel side on this end because I know I want more zeros. Put the series side on that end because I know I want it to be fairly difficult to get to 1. And A needs to control 2 of these, and B needs to control 2 of these, and that is not a terminal. I'm going to redraw that carefully. And here's my kind of connection point right there, where it could have gone either way. So keep in mind too, that we can get PNP or NPN. And so I'm going to check, let's set these up to be PNP. And these to be NPN. I'll explain why in just a second. So that these two transistors operate under exact opposite conditions of these two. So NPNs, they turn on when the input is low. So these turn on when it's low. And these ones turn on when the input is high. On when it's high. So it's good to kind of remember when they turn on, when they turn off. Now all we're going to do is we're going to trace some of these logic functions so you can see how this works. Let's start with this one. I'm going to do that one in green. Okay, so A is a 0. And so let's see, when it connects to here, this one turns on when it's low. So this gate is turned on. Current can flow through here. So this connection goes through here because this one is on under those conditions. Meanwhile, B is high, so this one is off. So it cannot also connect through here, but that's okay. We already connected C to ground. We're definitely getting a 0 out already. What we also want to check though is we don't have a short circuit from 5 to ground. That would be bad if current can flow directly down this path. Let's make sure at least one of these is off. Let's see, this one is on. Okay, that's not good. But this one is off. Okay, this one only turns on when it's high, but we put a 0 in this side. We put in a low. This circuit is off. So can I get from C to the plus 5 volts? No, I can't get through that. This thing is off. Okay, so it shuts off this entire pathway. That's one possible scenario. Let's trace another one. Let's do this one. I'm trying to trace backwards from what can C connect to? Can it connect to here or can it connect to here? And let's, I'm not going to erase everything, but let's just switch to blue here. Okay, so this is a 1 and this is a 1 now. Okay, so if this is a 1, these turn on when they're low, but we now have a high input. So this is off, and this is off. Can C connect to ground? No, this is off, this is off. C cannot connect to ground. C is not supposed to be a 0 at this point. Meanwhile, this is on, this is on. Can C connect to high? Yes, it can. It can go through this one and this one, and we've got C connected to plus 5 volts. So we're going to get a high output represented by that 1 there. All right, so that's an example of a transistor. Again, what I like to do is I like to think about the parallel side typically goes with where you get more of those outputs, and the series side typically goes with where you get less of those outputs. Oftentimes we're using 4 transistors to build each one. Not the case for all of them, but for a lot of them. I like to put in my inputs on the side, my output on the side, and then I like to also just have a plus 5 and a ground. And you can usually kind of figure out what goes in between. When you're analyzing them, try to think about what the outcome should be and work backward from C. Try to figure out, does C connect here or does C connect here? Which combination of gates are turned on that will allow it to connect to one of those two, but hopefully never both spots. Because if we had both spots open, we'd be just shorting power right through here. That'd be bad. Okay, so here's a bunch of cleaner drawn out ones. What I recommend doing right now is grabbing some scratch paper, copying down one more of these gates, take your pick, setting up a truth table and a Venn diagram adjacent to it, and then trying to trace your way backwards from where does the output connect to under different conditions. Remember that the PNP gates turn on with a low input, and the NPN gates turn on with a high input. It's the same input as whatever the middle gate says. Or sorry, middle doped region in that set of 3. So hopefully you're like, okay, I kind of sort of get how transistors work now. Hopefully you paused the video and actually practiced at least one more time on some of these other samples that are drawn up here. You can copy the structure and just try to trace backwards once you got a copy down from that logic gate. That's a great way to practice understanding how these work. Okay, so here's some vocab. We talked about a whole bunch of different kinds of logic gates. Talked about understanding using a truth table, which is that table of inputs, outputs, zeros, and ones. Venn diagram, shaded regions. We haven't talked about compound logic yet. This is when you use more than one gate together. Maybe we'll do that in a sec. Although if you guys are in my IB course, our IB textbook honestly does a super good job of this. One of the few times I'd totally recommend going to the textbook first on this part. Let's see, we talked about transistors have 3 doped regions while diodes only have 2. They're set up by adding holes or extra electrons to a silicon or germanium crystal, a semiconductor, and then allowing those holes to migrate across the junction, setting up an electric field across that, as well as a depleted region where stuff is generally stuck. We talked about naming conventions. Depending on how they're manufactured, you'll hear some kind of a word for electrons go in, electrons come out, and the thing that turns it on or off. Examples are source drain gate or emitter collector base. Real quick, let's talk about analog versus digital. Transistor in digital mode, it should be either on or off. So we basically want full resistance or no resistance, or as high or low as that resistance can go. We're going to max it out to one of the two extremes. And there will be some point at which you have to decide, is it a 1 or a 0? And computers will be operating at voltages as far as possible from that decision point, and they'll be giving it time to settle to one side or the other side. So we won't ever hopefully be in an ambiguous situation, because if we are, that's when the overclock you put on your CPU is going to crash you. That's bad. Don't do that. I mean, do that carefully and make sure you know what you're doing. Okay, but in analog mode, let's talk about this. So let's say you have a dinky little phone and you want to power like 1,000-watt speaker system. So you got your output, and let's just graph. Here's some music on your phone. That's like your favorite artist singing right there. What we want to do is we want the voltages as well as the currents to be much bigger than on the speaker, like little tiny headphone output from your phone. We want to amplify that signal. So on a wave, amplitude is the y-axis. And in this case, it's going to be measured in volts. So we're trying to get more voltage and more current through here. What I can do is I can have a giant power supply that's able to put out tons of voltage and tons of current and tons of power. And what I want to do is I want to basically be able to control how that's working. So I'm going to put the phone's output as just a little tiny bit of voltage needed to adjust the resistance of this. And this isn't just on or off, hard to one side or hard to the other side. This can also be any of the values in between. So as the voltage of the phone goes up or down, the resistance of this transistor is going to go up or down, and it's going to control the current and power coming out of the supply. And this is going to go to that crazy giant speaker system at the rock concert. This is, by the way, this is grossly oversimplified. There are more parts in an amplifier than just this. But this is the concept. We can use a tiny control voltage to change the bias on this and change the resistance of that, and thereby control a much larger current with a lot more power in it. That's kind of the idea of how we'd operate this in analog mode. We're not just hard to one side or the other side. It can also be any value or range in between. All right, let's keep going. So now we've got transistors, we got logic gates. Let's see if we can actually add stuff and make the simplest of all basic computers. So let's try it. Let's add some numbers. Let's just jump right in. So let's say I have 7 plus 5. I'm in decimal right now. That's going to be 12. Or I'm going to set up an 8-bit register. I'm going to use 8 digits of binary. And I'm going to figure out what 7 is. Let's see, 7 is going to be 4 plus 2 plus 1. So I'm going to start from the left. Here's my 1's digit, 2's digit, and 4's digit. There's 7. And here's the remaining digits in that register. Perfect. And then 5 would be a 4 and a 1, right? So there's 5. Okay, let's add. 1 plus 1, that's a 2, but I don't have 2's because it's binary. So I'm going to start over and carry. And 1 plus 1 plus 0, that's also going to be a carry and start over. And now one of these is going to carry, and I still have a 1 left. So I'm going to put that there. I'm going to put that there. Oh, just kidding. That was a 1. I'm sorry. That was a 1 because, there's 3 of them there. And I've also got to carry this down. And there we go. And let's see what's that worth. That's an 8 digit, and there's a 4's digit. Yep, we got 12. So adding, Easiest thing, super easy, not a problem. Okay, subtracting, we're going to learn a method called 2's complement. I'm going to get you guys the concept first. Concept is just a little bit weird. And then we'll come back to the actual procedure for it second. So I had this dream once. I was trying to, how do I explain this? Because what to do is easy, but why we do it is pretty confusing. And then I was trying to explain this, and some students were asking really good questions. I didn't have like a crystal clear answer. But then one night I had this dream. There were all these melted clocks. And I'm like, yeah, melted clocks, Dali. That's the ticket. So here's the plan. We're going to deliberately use the concept of overflow. Overflow is we have this 8-bit register. What happens if stuff carries out to the 9th digit? Problem is there is no 9th digit. So if it carries off the end of our register, it's gone. That's overflow. The other idea we've got is modulo, which is when you're dividing by a certain amount, what's the remainder? Not necessarily like the dividend, but just the remainder of that. So we're going to start to think in terms of a conventional clock first, and then we'll look at a weird clock that goes all the way up to 255, and then we'll come back to the procedure of what 2's complement is. So we got a clock. This is 12 or 0, however you want to think about it. And right now, our hours hand is sitting at 1 o'clock. How do I subtract 2 hours from this? What are my options? Well, we know the answer should be 11. One option is we try to subtract 2 by moving the hand 2 hours to the left. But that's weird. We just crossed over this and we just kind of like, how did we get to a big number from a small number? And if we had negatives on a clock, would you know this is -1 now? Not really, right? It just looks like you're back at 11 again. So on a fixed register size, this would be kind of confusing to do. You know, the other thing you could do, the other way to get to 11 isn't to subtract 2, it's to add 10. Okay, so we could also do that, and we could push this thing the other way. So hopefully that's kind of an interesting concept. We're basically, whenever we get to 12, like every time we count up to 12, we take away 12 before we keep going. We've overflowed some numbers. They don't fit on a 12-hour clock anymore. Like if we're on military time and it's supposed to be 13 o'clock, it's not going to show 13 o'clock. It's going to overflow 12 and it's going to show 1, right? That's 1 p.m. The other thing we're doing is every time it's a number bigger than 12, we're dividing by 12 and we're only keeping the remainder. That's the modulo perspective on how this all works. So yeah, keep in mind, we can push things all the way around to the right, a big amount, and that would be the same as pushing things a little bit to the left. Just to make sure you got this, let's say we got this clock again. And it is hours pointing to 6, and I want to subtract 7. What are my options? One option is I could try to subtract 7. Another option is I could add 5. And those both end up at the correct spot. So we can add instead of subtracting, and we use a complementary number to however this thing tends to overflow, however far around we need to go. Now, let's say I'm working with the 8-bit register. The number up here isn't 12 anymore. What's the biggest number we can represent with 8 bits? Let's see, isn't that, here's a 1, a 2, a 4, a 8, a 16, 32, 64, 128. If I had all of those, total is going to be 255. So I could think of this as a clock with 255 instead, and I could use these same principles to subtract and add, only I wouldn't be targeting the complement to 12, I'd be targeting the complement to 255. Okay, one more layer of possible confusion. We're going to be working with signed bits so that we can represent negative numbers as well. So on my 8-bit register, 2, 3, 4, 5, 6, 7, 8. Okay, this is still a 1, that's a 2, that's a 4, that's a 8, that's a 16, a 32, and a 64. This is not 128 anymore. On a signed register, the leftmost digit represents if it's a plus or a minus. Zeros are going to be positive numbers. Ones are going to be negative numbers. So if you see a 1 in the leading digit of the register, this rest of this number is a negative. And what this means is we don't go from 0 to 255 anymore. What we go from is negative 128 past 0 up to positive 127. So by using a signed bit, we've shifted the entire register 128 to the left. We still have 256 possible total digits, but they're centered on 0 instead of starting from 0, using this digit on the left side. So with all that in mind, let's bounce back to this idea. How do we do subtraction? A lot harder than adding. So we have an algorithm to follow. It's really easy to follow, actually. Write down the number you're subtracting, the number that's negative, basically. And if you want to represent a negative number, we're going to flip every digit. So all zeros become ones, all ones become zeros. And we're going to add 1. This may like ricochet carry down the line some, whatever. And this is now a negative number written as a 2's complement. This idea of going around the clock the opposite direction. Instead of subtracting numbers, we're going to be adding complementary numbers that get us the same distance around the clock in the opposite direction. So we can still add them. So let's try this. This time, we're going to be working with 7 minus 5. We're going to try a negative number this time. So I'm still going to write 7. Here's my 4, 2, and 1. Now I'm going to try to write 5. I'm going to go over here for a sec. So let's see. 1, 2, 2, 2, 2. That's positive 5. To do 2's complement, step 1 was flip every digit. Step 2 was add 1. Okay, this is negative 5 written in 2's complement. Now you see we could have subtracted a really small negative number, but instead we're going to go the opposite direction around the clock and we're going to add a really, really big number. And let's see what happens. So I'm just going to set up 2's complement and then I'm going to add. And if we overflow, that's the whole point. We've made it all the way around the clock and past that spot where modulo kicks us back down to some smaller number. We overflow some stuff. So 1 and 1 is a 0 and a carry. 1 and 1 is a 0 and a carry, but there's an additional 1. 1 and 1 is a 0 and a carry. 1 and 1 is a 0 and a carry. And this thing ricochets all the way down. And we're carrying out. But this goes nowhere. It's gone. It overflowed. It went past the register. There is no place to store that. It's gone. Hey, what do we have here? Check it out. That's a 2's digit. 7 minus 5 is 2. So it works. This algorithm is great, and hopefully you kind of understand how we got this algorithm and why it's working. Okay, now the thing that freaked my students out, that got me dreaming about clocks, was this monster. Bum, bum, bum. All right, let's try this thing. So I'm going to write down 9. There we go, that's 9. I'm going to follow the 2's complement process. Step 1, flip every digit. Step 2, add 1. Okay, this is 9 written in 2's complement. And let's write down 9 and let's try to subtract from 7. Let's see, yep, that's still 7. Okay, and now we're adding using 2's complement to do what was actually subtracting. So that's a 1 and a carry, a 1 and a carry, it's a 1 and a carry, that's a 1. Those are all 1s. Oh man, what do we have here? That doesn't look like 2, does it? Wait, check it out. Is this a positive or negative number? Aha, this is a negative number. By the way, answer is supposed to be -2, right? Cool. So this is a negative number. Sweet. Now, in 2's complement, if these were all 1s, that would be the farthest around the clock we can go. Okay, so here's the clock again. We'll just pretend it's 12 up here. You guys are comfy with this. The farthest around the clock I can go only moves me the tiniest bit to the left. If these were all 1s, the smallest I can go to the left is -1. So all 1s is -1. This is a smidge less than all 1s. See how it's a smidge less now? There was as far as I can go. Here's a smidge less than as far as I can go. The fact that that's not quite all the way around the clock as far as I can go and still be a negative number, this must be -2. This is -2 written in 2's complement. So the algorithm's still working. Just don't freak out when you see a whole bunch of ones and you're like, but it was supposed to be a small number. No, the way this works is this is going way around the clock. And just however much less you have than going all the way around the clock is how negative it is. So again, this number, this is -1. It's the farthest you can go around. That's going around the clock, 256 spots, 255 times. We end up one to the left of where we started. That's -1. This is -2. It's all good. So yeah, that freaked me out the first time I saw it. I was expecting like, you know, a number that looked like 2. Like that. That when I think of 2 in binary, I think of that. So I was expecting a number like that, but with a negative sign on it, which I was kind of thinking I'd get this the first, get this the first time I did it. And so I was freaked out and a little bit flabbergasted when I got that. It took me a while to realize that in 2's complement, that's still -2. Just when using 2's complement, we still get a 2's complement answer. So look carefully at how your negative numbers show up. All right, I think that's it. If you want to learn how to multiply or divide, you can check that out in your own time. I don't think we need that just for our purposes. I almost forgot. Bonus track. There's a website called logic.ly. Without paying for it, you can't save your stuff, but it's a great place to go tinker. And we should actually set up some logic gates so that we can add stuff. So what I have up on the top left here, and this is part of the logic gates extravaganza excitement I have, is we have 2 inputs, A and B, just like as if we were setting up a Venn diagram or a truth table or whatever. We're going to have 2 digits that we can go in with. Also, sometimes we need to carry in from the previous bit of addition, so we got to carry in. We've also got a output, you know, that's going to be the digit that's the answer, and whether or not we carried out. So we're shown on the left here is a full adder. You can use a toggle switch to represent a 1 or a 0. So like 1 plus 1 is 0, but we're also carrying out. Or 1 plus 0 is 1, or 0 plus 1 is 1, or 0 plus 0 is 0. So you can see it's all working. Or if I carry in and have 1 plus 1, I have 1 and I'm carrying out. So we just went through like a whole bunch of different possibilities here for adding together 2 binary digits. Now, if you right click on these, and in the bottom right corner, you can go down and name each of these objects. Oops, just kidding. Right click on the side. See how you can go down here and name them? Once you've got them all named, you can highlight them, right click, and create an integrated circuit. What we're doing is we're saying all of these things are now one piece. We're abstracting that entire set into a simple block. Okay, so creating an integrated circuit, we're abstracting all, how many transistors is that? Let's see, 1, 2, 3, 4, 5. That's 5 logic gates. Each logic gate typically has about 4 transistors. So I think that's about 20 transistors right there to be able to accomplish this. We have 3 input wires and 2 output wires, and we also have a whole bunch of power in and power out circuits. So there's a bunch of circuitry going on here. But I can abstract that into one integrated circuit just like this. And then what I did is I set up an 8-bit register. This represents an 8-bit number for 1 byte. Here's another 1 byte number, and I can set them up to add just now by connecting A to B. And this thing, I am going to build a cascade. Okay, so think about it as a cascading waterfall. And I'm setting this up so that our carry in and carry outs work okay. So my carry out goes to my carry in. My carry out goes to carry in. Out goes to carry in. So I can cascade these across, as well as connecting in my next 2 digits. A, B, A, B, and so forth. I think this is one of the harder assignments on that worksheet, and I just want to give you guys a great way to do it. Keep it all nice and tidy and organized too. I'm not going to finish it, but you guys can hopefully get the idea and can see how you would finish it. Anyway, in the long run, we're going to have this thing, and we're just going to connect. Here's the first digit, second digit, third digit, the fourth digit. Oh, they want all inputs accounted for. They're not happy about this missing carry in. So I'm just going to say, oh no, on the first digit, we never would have carried it. That doesn't make any sense. It makes that red line error go away. And yeah, hopefully you can kind of see what I'm doing. This can represent numbers up to 8. And so this is basically a nibble right here. We're going to need 2 nibbles to work with a full 8-bit register. And so you can interpret how these 2 numbers together, what that value is. But let's try this out. So 1, yep, there's 1 plus 0. Here's 1 plus 1. Here's 2 plus 1. Here's 2 plus 3. Here's 2, that's 3 plus, oh, no, just kidding. What is that? Oh, I'm sorry. That's 6 plus 3. So yep, everything's working. So we should be able to get numbers up to 16 here. This is basically in hexadecimal. Actually, let's do that. Hey, there we go. There's some hexadecimal goodness for us. Okay. Anyway, just in case you're on that assignment and you're having questions, just look up a full adder with a carry in and carry out capability, and then abstract that into an integrated circuit and use that repeatedly in this cascade pattern. By the way, when you wait for the output, this one can't do its thing until this one is done. This one can't do its thing until this one is done, right? So we need to wait for the cascade to happen before we check for the answer. If we check for the answer too soon, and some of these are done, but it hasn't cascaded all the way down because that takes some time, that's when your CPU is going to throw an error and your computer is going to crash, and you need to lower the clock speed to give it more time to finish computations in between checking each cycle. So if you're an overclocker, hopefully you're starting to be like, oh, I kind of get what's going on. Yep, and then last up, check yourself that you can switch between a truth table, a Venn diagram, or if you make extra chill ones, maybe a Zen diagram, a circuit gate diagram. You can also describe what's happening. So you should be able to convert between those different ways of thinking regarding our Boolean logic. And hopefully you know some vocab words and you can describe how transistors are built and how they operate, how they're arranged to make those gates. And you can describe how to add and subtract in binary, including using 2's complement to do it. Yeah, hopefully you watched that video, got a good couple chuckles out of it too. That video's awesome. I think that does it for today. Hopefully that was helpful. I'm Mr. Worden. Thanks for watching, and I'll see you guys next time.